one more minute and we'll get started. So I'll just read your bio here.
All right.
So our first speaker is going to be Mr. Gibbons, Randy Gibbons. He has a BS degree in chemistry from the University of Houston. He has 40 years of experience in chemical measurement systems design and implementation, including 30 years of experience advancing open path spectroscopy systems. Mr. Gibbons is one of the founding partners of what is now Terra Applied Systems LLC. TAS works with manufacturers and end users to promote new and emerging technology applications. The TAS team has over 100 open path projects in service, including most of the operations critical open path HF and ammonia laser monitoring systems in the Americas. Most of the Fenceline monitoring systems in California, working in conjunction with Sonoma Technology. The laser H2S monitoring advancement is a TAS initiative with notable support from Unisearch Associates, ETAS customers, and Sonoma Technology Inc. I'll just introduce myself. I'm Marty Sparks. I'm with Max Analytical, and I'll be moderating, and the floor is yours.
That sounded too much like a commercial. But it is where I came from. Talking about H2S laser gas detection. It became, I'll go through real quick with a little introduction. I guess we're going through that now. Go through a little bit of the roots of the tunable laser spectroscopy technology that we're working with on early installations. And where it started to get the opportunity to develop it was in California initiative. Talk about the technology and how it's improved and where we're going. The whole goal, like the title says, is Fenceline is nice, but there's a big market out there that's not Fenceline. It's in refineries and chemical plants where they have H2S issues. And that's where a lot of the people for years have been trying to get to. So Terra Applied Systems is my company. It's for about 30 years now. Been doing Fenceline systems. We did the first California Fenceline installation in the 1990s. And we've done a lot of laser work with 4L laser research and others. And then real quick, Unisearch Associates, it's the equipment we've been using to do the better H2S work with. It's a Canadian company out of Toronto. They were founded, I think, in 1984 or something like that. But they've been around a long time doing laser spectroscopy. Kind of the players. So the background, the roots of open path laser systems, there was a lot of development in it in the late 70s and 80s. And a lot of these guys who run the laser companies these days, helps form them, or came out of the same efforts. So a lot of them on Southwest Research, and then they kind of split off into other companies. Some of them forming their own, some of them working on. Comes from a core group of them. And some of the first area monitors using the open path, some that came out of Southwest Research, who I don't remember who bought the business from them. The first ones were mostly HF alkylations. It was a high critical installation, high critical measurement, maybe fast measurement. And those were somewhat successful, but there were improvements after that. So the first real open path H2S installation permanent was their refinery, Unocal at the time. And that was our project, and we were awarded it. We were to identify vendors, and Unisearch was the definite front runner on that when it was handed to us. But they said it was going to be $450,000 per gas per path, and they wanted to more or less take over the project, which neither of those sounded very good to me. And so we ended up doing some investigation, and 4L Laser was doing some work out of the University of Alberta. And they weren't commercial, but I talked to them for about 2 months and convinced them to sell the first 4 commercial units into that installation. So there were 2 H2S lasers and lasers on our Fenceline system. And this is 1996. And those were Boreal systems. And H2S is still in service, but about to be changed because The use of H2S open path has been fairly limited because the sensitivity is not good because you get to low levels and so we'll talk about why that happens. But again, first installation we did at Unical, and then Chalmette Refining, Chalmette, Louisiana. They have a sour gas cooler that they was leaking, so it was a good application. It was high H2S. ExxonMobil Torrance Refinery has H2S in a basin area for worker safety. Needed a ideal H detection. And then there's an ERG sweetening plant just south of San Antonio, the high sulfur gas plant. So we put one in there to monitor. It had to be high concentration. Then it had to be the right application for it. Some others around, there's one in Venezuela, but those are the ones that. So in California, they've been operating, another company took over operating Fenceline system in the early 2000s after we did our thing. And the Boreal said what they thought the detection limit was. They never did anything to prove it at first. And by the time we handed it off, it appeared the detection limit wasn't quite near that. So the new contractor was reporting for several years of detection limit parts per billion on a 900 meter path, and it wasn't anywhere near that. And so they wrote the regulations for the Fenceline California. They wrote in that 30 parts per billion, and there wasn't the technology to do it. I didn't do about it. And so it became known that Boreal could, and Boreal told them it did, and we had told some of the other people that it couldn't be done. So it became a big deal, and Unisearch was identified as a prospective unit that could do it. They go about the spectroscopy. We looked at it and said Unisearch was unproven on the H2S application. It was a good product, it was a track record, but it was unproven. California specs were still a little bit fuzzy, so started to commit to it, and it looked like we needed to do some work to build a data system to take the Unisearch data and put it into a format that was usable for maybe just a 5-minute report. And from our perspective, our interest in investigating this independently was not the open path Fenceline market, but it was the short path around refineries and chemical plants where there's a real need, we think, and that's where a lot of the early laser people were looking for, and it looked like there might be opportunity to actually do that. And so we built a test system and started running it, and started to work out the kinks on how things need to work, both for the Fenceline applications around smaller areas. Real quick tutorial on the spectroscopy. Boreal and most of the other partial lasers use what's called wavelength modulation spectroscopy. They take the laser and they oscillate it so they get a sine wave carrier, and then they rank that oscillation across an absorbance band. So that's what this is supposed to show. You get a laser that's oscillated over a ramp, put it into the gas, and you get a signal. It's not really like that. And then the spectrum that comes out, most of them right now are using triplet peak. So this is the signal they're looking at. And sometimes I'll do a peak height on that. Sometimes I'll do a peak curve on that, or an integration area for the measurement. But that's the signal they're looking at. It's really good, really nice, except for one thing. Have two gases that absorb in the same region. You have two triplet peaks that overlap each other. And not only that affects, there's two things that affect the performance of the laser that are kind of critical. One of them is temperature. And so this is a map of the temperature ramp. The other thing is the modulation depth, which is the amplitude of that modulation on the carrier. And so that affects the performance also. So you end up with a field that you need to tune in to try to isolate one peak or one measurement feature. and it gets really nasty. So wavelength modulation, this is why they can't do the low levels of detection, just with pure wavelength modulation. That's the low concentrations. So that's what all that says. So you have to have a high rate, very high ratio of H2S, and the atmospheric contamination that's a problem is water, primarily water and carbon dioxide. So you have to have a very high ratio of H2S to those before you can really make it. So that's why the sour gas application. But not the very high detection that they needed for Fenceline. So what Unisearch did, and the story that they told me is they had a project and they were having trouble meeting spec on it because of the wavelength modulation problem. So they went and coded a direct absorbance algorithm into theirs. So that instead of having the modulation where you effectively take the first or second derivative of the peak, they can measure the absorbance directly with the laser without the modulation factor. And so you get a peak that looks more than there is a normal absorption peak. Just a peak get out of a regular spectrometer. So this is the shape of the feature of the H2S that they're looking at. They have the H2S peak, which is here. Then they have water, carbon dioxide that's off to the side. Water actually spills into the edge of this peak here. And so that's where there's problems with the wavelength modulation, all those overlaps, and trying to pull the influence of the water, especially, out of the measure. So this is the signature that we get out of the Unisearch, and it can be easily fit using your standard spectroscopy methods like you do with the OpenPath FTIR or FTIR in general, and it's UV. So just real quick how they go through it. This is the ramp across the peak feature that they're looking for, and you can see it's not modulated, it's a straight ramp. And take that and they construct a baseline curve that they're measuring, and then you can see the black or the blue rather is from the peaks overlaid on that baseline. So they can construct a baseline to do an absorbance calculation. So then they can fit the individual pieces. And this comes out of their software. It's really nice. There's not much H2S in the sample. There's a little bit of a baseline construction. You have the water measurement, carbon dioxide. You measure all three gases with the absorbance. So we're making a measurement every 8 seconds. It could go a little bit faster, but it gets noisier. It goes slower, but 8 seconds. In 8 seconds, you have to watch that baseline change. So we're doing a faster measurement to make sure that we keep the baseline updated. So this is what we've been seeing out there in the Fenceline system. The orange is our H2S measurement, and this is in parts per billion. I don't know, 940 meter pound. So it's essentially we're getting about 3 sections. But you can see there's a little bit of noise, which is a feature that a lot of the laser people have to deal with. But we check it for spikes and things like that. We do some analysis for that. But the baseline detection, our detection limits are running around 3 parts per billion. Also measuring the water, 2 reasons. It's a check on the fit for the H2S measurement, and it's also a permanent gas in the atmosphere to verify it's in a reasonable range where it should be detected. So it's a real-time check gas. It's a co-detection. This is a plot of the detection limits. And this is the whole story behind all of it. Kind of detection limits, especially on a short path. So plot of detection limit, calculated the detection limit real time over versus time. And you can see that all punches well, almost all punches well below parts per billion. And this one calculates out 2.5. So what this did from the Fenceline perspective is we've proven the commercial system will do it. There's another system, the Air Optic, they have a development system that they run out there. We've run 7, 8. We run 8 different paths out there. 6 of them are running full time. 1 of them is still running as a demo, and they're all running pretty much the same way. So that's something that we, with the commercial system, that's one of the things. From an engineering perspective, you don't want an experiment out there. You want a commercial system with a proven background, from my perspective. Anyway, and it's doing everything that the regulators out there have requested it to do. Part of this is we're doing a little bit of post-processing on it. InnoSearch doesn't have a lot of cleanup algorithms in theirs. They'll do some averaging and things like that. But in the open path with the lasers, we can get some pretty large spikes when we have low light conditions. And the customer was very sensitive to transient false positives. And so we had to monitor, and we do monitor the instrument conditions, path conditions, and we monitor each detection as it comes in, and we compare it trending against real-time detection limit, as well as the spectral noise, and we identify something as an aberration, and we'll mark it or eliminate it if necessary. So when we look at that plot back here, on this, these are low light conditions where there's a weather event, or there's fog, or moisture in the morning. This one, we actually had some water rising on the reflector, which we haven't to address. So most of these are just signs. We've got pretty well handled. They're all, one exception, they're less than 25 parts per billion, which is just a single spike, which is the detection limit we have to be 25 parts per billion on this 1,000-meter round trip path. So that's okay. And again, so is the Fenceline. All goes beyond that. But right now, we've been through testing. We've run these systems. We understand the design requirements, make sure that they're stable, control the noise factors. We know what the measurement methods are and how to configure them and get them to work reliably. And we know the detection limits are adequate on long path for safety monitoring. Now there was a question as we shortened the paths, we tended to get more noise. And so going to shorter paths like we do HF monitoring, ammonia monitoring, to more like 10 to 100 meters, started to get noisy. But we've been working out with the reflectors and how to configure reflectors use for the reflector. That noise is showing similar detection limits on a meter basis. So we can, on a 5-meter path, our detection limit is somewhere around 0.2. So that starts to get a lot more interesting for HSE. And so what we're working now is their transceivers, their transceiver scopes are fairly large, and from a practical perspective, other applications, we're working to reduce the size on those, get them down to something that's more on the order of a bread box or smaller. And we've got some test units running now. And we'd like to put them out there and test them. We'll do some testing, of course, around our shop based on it, but hopefully soon we'll be ready to test them in a real environment. And the other thing that's interesting about the InnoSearch, and this is different than the other lasers, they've either been, but they've all been needing hardwire both ends, or having what's turned into expensive cable with just basic Boreal systems. InnoSearch has a fiber to fiber in, fiber out. I guess I should describe it a little bit better. the way these things work is that leverage the cost of the laser and the electronics is they'll have a core unit that can send laser out to multiple locations and then bring the signal back to that one central unit. So it's like a distribution system. And that's what most of the systems that are like alkylation and ammonia units are like these days. And the return cable can get very expensive, and the hard conduit, two types of cable, possibly power, can get very expensive. And so we've got 2 installations, and we're putting more with the Unisearch running fiber optic to run the laser out, and then it converts the signal that would go over hardwire to fiber signal, and it's running it back. So it's going to improve the cost quite a bit. So from my perspective, there were several things that we have to address. We have to address the performance, which I tried to address here. We've got the detection limits for this unit. Performance standpoint looks very practical. You have to control the cost. And so the multiplexing and then better managing how the field devices, how much cost you have to put into field devices has been something we've been trying to address for years for all systems. And I think we have a pretty good handle on this. Pretty soon. So Fenceline, we leverage that experience to turn it into something that's a different market. We think probably more useful market for a lot of them. That's what I've done. Questions?